transformers have a specific voltage rating and a maximum volt-ampere capacity that they can handle. In this scenario, the transformer has a 480 volts primary and a 240/120 volts delta secondary, possessing a total capacity of 45 kVA or 45,000 volt-amperes. In a delta-connected transformer with a center tap, the neutral current is determined by the sum of the currents in the two 120 volts phases, referred to as cone and C2. The center tap serves as a common return path for both phases. The neutral current should be limited to avoid overloading the transformer. Excessive neutral current can cause overheating and damage to the transformer. As a general rule of thumb, the neutral current should not exceed 5% of the full load current of the transformer. This ensures that the transformer is not overloaded and that the neutral has sufficient capacity to handle the unbalanced loads that may occur. For this transformer, firstly calculate the full load current on the primary side by dividing the volt-ampere by the voltage. This is calculated as 45,000 volt-amperes divided by 480 volts, which equals 93.75 amps. Secondly, determine the maximum neutral current by taking 5% of the full load current. This is calculated as 5% of 93.75 amps, which equals 4.69 amps. Thirdly, calculate the maximum center tap 120 volts load by multiplying the maximum neutral current by the voltage. This is calculated as 4.69 amps multiplied by 120 volts, which equals 562.8 volt-amperes. Therefore, the maximum center tap 120 volts load should not exceed 562.8 volt-amperes, which is approximately 0.56 kVA, or about 1.25% of the transformer's total capacity. This ensures that the transformer is not overloaded and that the neutral has sufficient capacity to handle unbalanced loads. The 5% rule of thumb serves as a guideline for safely loading the center tap of the transformer. It is essential to stay within the maximum center tap load limit to prevent overheating and potential damage. Keeping the load within the limit helps to ensure a long and reliable operation. There are several factors that influence the calculation. These factors include the transformer's volt-ampere rating, the primary and secondary voltages, and the amount of the unbalanced load on the 120 volt center tap. The 5% limit is based on the full load current on the primary side, not the secondary side. The primary current is used as a base because the transformer is rated on the primary side. There are differences between the total transformer capacity and the center tap capacity. The total transformer capacity refers to the total power the transformer can deliver across all its secondary windings. The center tap capacity refers specifically to the amount of power that can be drawn from the center tap without overloading the transformer. Exceeding the 5% limit could lead to transformer overheating, reduced lifespan, voltage instability, and nuisance tripping of breakers. It's critical to adhere to the guideline for reliable operation. Also, the code requirements for center tap transformers is to follow local and national electrical codes, like the NEC, which provides guidelines on the installation and loading of transformers, including those with center taps. These codes are put in place to ensure safety and prevent electrical hazards. Here's a breakdown of how to properly size and calculate center tap loads on a 480 volts to 240/120 volts delta transformer. Firstly, determine the transformer kVA rating. In this case, it is a 45 kVA transformer. Secondly, calculate the total secondary volt-ampere. Since 1 kVA is equal to 1000 volt-amperes, then the total secondary volt-ampere is 45 kVA multiplied by 1000 volt-amperes per kVA, which equals 45,000 volt-amperes. Thirdly, calculate the maximum allowable volt-ampere on the center tap. As stated, the maximum center tap load should not exceed 5% of the total transformer capacity. Therefore, calculate 5% of 45,000 volt-amperes, which is 0.5 multiplied by 45,000 volt-amperes, which equals 2250 volt-amperes. Fourthly, calculate the maximum allowable current on the center tap. Using the formula amps equals volt amperes divided by volts, calculate amp switch equals 2250 volt amperes divided by 120 volts, which equals 18.75 amps. This value represents the maximum current that can be drawn from the center tap without exceeding the 5% limit. Therefore, the maximum center tap load is 2250 volt amperes or 18.75 amps at 120 volts. These values should not be exceeded to prevent overloading of the transformer. Also, the NEC addresses transformers with center taps in sections like 450.3, which covers transformer overcurrent protection. The NEC mandates that transformers be protected against overcurrent, which could arise from excessive loading of the center tap. The specific overcurrent protection requirements vary based on the transformer size, voltage, and application. For example, for transformers rated over 600 volts nominal, the primary overcurrent protection should be set at no more than 125% of the transformer's rated primary current, according to NEC 450.3. Likewise, the secondary overcurrent protection should be set at no more than 125% of the transformer's rated secondary current. Also, NEC 220.61 describes the permissible loading of a neutral conductor and its connection to the center tap. The code specifies requirements to ensure that the neutral conductor is adequately sized to handle the unbalanced load it carries. The NEC emphasizes the importance of proper grounding to mitigate the risk of electric shock and prevent equipment damage. For delta Y transformers with a center tap, the neutral point must be grounded in accordance with NEC 250.20 and NEC 250.26. Also, using a three-phase power analyzer to measure the currents in each phase, including the neutral, can ensure compliance with the 5% rule. Also, infrared thermography can be used to detect any signs of overheating in the transformer windings, connections, or core. This can help identify potential issues before they become major problems. As a general rule, transformers should be inspected regularly for signs of damage, overheating, or corrosion. Regular maintenance, such as tightening connections and cleaning the transformer, can help ensure its reliable operation and prolong its lifespan. To ensure compliance with NEC guidelines, it's best to consult with a qualified electrician. The electrician will be able to perform the necessary calculations and measurements to ensure that the transformer is properly loaded and protected. In summary, adhering to the 5% rule for center tap loads is essential for the safe and reliable operation of delta transformers. By understanding the underlying principles and following best practices, one can avoid overloading the transformer and ensure a long and trouble-free lifespan. Let's delve a bit more into the reasoning behind the 5% limitation on center tap load in a 480 volts to 240/120 volts delta transformer. The 5% rule is not an arbitrary figure. It is derived from a combination of factors, including the transformer's design, the characteristics of the delta connection, and the potential for unbalanced load. Firstly, the transformer's design characteristics affect the 5% rule. Transformers are designed to operate within specific thermal limits. Exceeding these limits can lead to overheating, insulation breakdown, and premature failure. The center tap winding is typically smaller than the main secondary winding. Therefore, it has a lower thermal capacity. By limiting the center tap load to 5% of the total transformer capacity, the risk of overheating the center tap winding is reduced. Secondly, the delta connection is a factor. In a delta-connected transformer, the line-to-line voltage is equal to the winding voltage. This means that the voltage across each phase is the same. However, when a center tap is added to one of the phases, it creates a potential for unbalanced loads. If the load on the center tap is too high, it can cause voltage imbalances in the other phases. This can lead to reduced performance and potential damage to connected equipment. Thirdly, unbalanced loads are a factor. In a three-phase system, the ideal scenario is that the load is equally distributed across all three phases. However, in practice, this is often not the case. Unbalanced loads can cause current to flow in the neutral conductor, which can overload the transformer and lead to voltage imbalances. By limiting the center tap load to 5%, the amount of current flowing in the neutral conductor is minimized. This helps to prevent overloading the transformer and maintain voltage balance. Now let's look at another example. Consider a 75 kVA transformer with a 480 volts delta primary and a 240/120 volts delta secondary with a center tap. The total secondary volt ampere is 75 kVA, which equals 75,000 volt amperes. The maximum allowable volt ampere on the center tap is 5% of 75,000 volt amperes, which equals 3,750 volt amperes. The maximum allowable current on the center tap is 3,750 volt amperes divided by 120 volts, which equals 31.25 amps. Therefore, the maximum center tap load is 3,750 volt amperes or 31.25 amps at 120 volts. Another important concept is the difference between single-phase and three-phase loads. Single-phase loads are connected between one phase and neutral, while three-phase loads are connected across all three phases. Single-phase loads contribute to unbalanced currents in the neutral conductor. Therefore, it is important to limit the amount of single-phase load connected to the center tap. Three-phase loads, on the other hand, are balanced and do not contribute to neutral current. Therefore, they can be connected to the transformer without affecting the center tap load limit. Also, the location of the transformer can affect its performance. Transformers should be installed in a well-ventilated area to prevent overheating. The ambient temperature can affect the transformer's ability to dissipate heat. In hot environments, the transformer's capacity may need to be derated to prevent overheating. Now, let's consider the impact of harmonics on the center tap load. Harmonics are non-sinusoidal waveforms that can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause increased current flow in the neutral conductor. Therefore, it is important to mitigate harmonics to prevent overloading the transformer. One way to mitigate harmonics is to use harmonic filters, which are designed to block harmonic currents from flowing into the transformer. Another way is to use a K-rated transformer, which is designed to withstand the effects of harmonics. Also, the utility grid can affect the transformer's performance. Voltage fluctuations and other grid disturbances can cause the transformer to operate outside of its design parameters. It is important to protect the transformer from these disturbances by using surge protection devices and voltage regulators. In some cases, it may be necessary to use a power conditioner to clean out the power before it enters the transformer. Proper grounding is critical for the safe operation of a transformer. The grounding system provides a low impedance path for fault currents to flow back to the source, which helps to prevent electric shock and equipment damage. The grounding system should be designed in accordance with NEC Article 250. There are several types of grounding systems that can be used, depending on the application. Common types of grounding systems include the solid grounded system, the impedance grounded system, and the ungrounded system. Each type of grounding system has its own advantages and disadvantages. Choosing the right type of grounding system depends on the specific application and the level of protection required. Also, surge protection devices can protect the transformer from voltage surges caused by lightning strikes, switching events, and other disturbances. Surge protection devices should be installed on both the primary and secondary sides of the transformer. There are several types of surge protection devices that can be used, including metal oxide varistors, silicon avalanche diodes, and gas discharge tubes. Choosing the right type of surge protection device depends on the voltage level, the surge current capacity, and the response time. Also, voltage regulators can maintain a constant output voltage even when the input voltage fluctuates. Voltage regulators are used to protect sensitive electronic equipment from voltage variations. There are several types of voltage regulators that can be used, including tap-changing transformers, electronic voltage regulators, and ferrosonant transformers. Choosing the right type of voltage regulator depends on the voltage level, the voltage regulation range, and the response time. Also, power conditioners can filter out noise and harmonics from the power supply. Power conditioners are used to protect sensitive electronic equipment from power quality problems. There are several types of power conditioners that could be used, including isolation transformers, line filters, and uninterruptible power supplies. Choosing the right type of power conditioner depends on the type of power quality problems that are present. Understanding the potential issues and implementing proper safety measures will lead to a successful install.